All right, MAP4C, day 46. Yesterday we were talking about quadratic models. Today we're talking about exponential models, and uh, the 3-minute review is a review of yesterday's stuff. So how can you tell a function is quadratic from the graph? Well, the graph is a parabola, right? As long as we can recognize a parabola, we can tell that it's quadratic. From the equation, well, the equation, remember, looks something like this. It's got a squared in it, right? Where A, B, and C are just numbers. So it might be something like, decimal 5x squared minus 3.2 or something like that. Then B would be 0 in this case. But when we see an x squared in it, that means it's quadratic. From the table of values, remember the second differences in a table are constant. And so today we're going to see if we can recognize exponential models in these three ways, from the graph, from the equation, and from the table of values. Here we go. Determine distinguishing characteristics of exponential models in a real life situation. So let's get at it. What is the graph of an exponential? We got two types of exponential models: exponential growth and exponential decay, and we're going to talk about the differences between them. An exponential growth function, I should be using a ruler here. That's terrible. Just terrible. Going over here too. Exponential growth, starts slow and then becomes more quick. It kind of looks like a parabola, but it's steeper than a parabola. Exponential decay is the one that looks like that, right? Or it decreases quickly and then more slowly, and it never quite ends up 0. From the table, and I'm going to write down an example of a exponential function. And the idea of an exponential model is the differences. If I were to do the differences, they're not constant. The first differences, second differences, third differences, whatever. But how am I getting the next value? Is I'm multiplying, right? So it's not that there's a common difference. There's a constant ratio between terms. And the way I could find it, I see I'm just multiplying by 3, but if I couldn't see that, I'd go the second one divided by the one before it, and each of those is a constant ratio of 3. Constant ratio. Over here. And when we're modeling real life values, they won't be so nice usually, but like such nice numbers, they'll be decimals and stuff, but we'll be okay. We'll get there. So who knows what this y value is, but we can see it's getting cut in half. And if we wanted to think of it in terms of the constant ratio, well, I'd go second one divided by the one before it, and that's 0.5. And because this constant ratio is less than 1, it's a fraction, that gives it a decay. So when the constant ratio is a fraction, that shows it's a decay function, okay? So a decimal or a fraction. Well, what does the equation look like? I don't know if you remember this, but it kind of looks like this. And what are these things? Well, A is the initial amount. And B, well, B is the base, and it's also the common ratio. Common, that's supposed to be the word common. We also sometimes, and maybe you can squish this in here, we sometimes write this a growth function, and you might remember this from grade 11, as 1 plus r to the exponent x, where r is the growth rate, that's the percentage. And as long as this value is a plus r, this b will be more than 1, and then it'll be a growth rate, okay? And this is a growth rate. Over here, in contrast to that, a decay rate would be 1 subtract r to the exponent x, where r is the rate of decay, how much it's decaying every year, but it's still a percent. More often than not, I'll just write it as the same thing here, right? It's still the initial amount and the base, but this base here, this time, is going to be less than 1 for a decay. Again, same as the constant ratio. It's less than 1. It's a fraction or a decimal. Okay, base is less than 1, a decimal or a fraction. And there's like a 5-minute version of what you talked about in grade 11 about exponential functions, and we'll see them in action here in a second. So, is it an exponential function? So, how do we know it's an exponential function? Well, let's see if they have a constant ratio. Our x's are all going up by the same amount. Do we have a constant ratio? If I go 24 divided by 20, that gives me 1.2. 28.8 divided by 24 is about 1.2. 34.6 divided by the one that comes before it is about 1.2. Yeah, constant ratio, yes. And even better than that, because I've got the y-intercept, this is the initial amount, and then it's going up by a little bit every year. So I could actually write this. This is an initial amount of 20, and the base is 1.2. And I can see here, this is the initial amount, this is the base. Also in the other version, the a1 plus r, you see 1 plus r, the r is 0.2. So this is a growth rate of 20% per year, or per month, or whatever x value is. Okay, so file that in the back of your mind, okay? It is an exponential growth. But what about this one? Well, if I go, it looks like it's a decay function, right? Because it's going down. But if I go 285 divided by 300, fire that into a calculator, and I get 0.89. Looks like it's a decay. But if I go 250 divided by 285, that's 0.88. This one is 215 divided by 250. You wouldn't have to write this down every time if you just wrote the common ratio or the ratios. That would be good enough. So this is the common ratio, and no, I see the not constant ratio. And I think actually it's close. It's close. We might be tempted to say that's the same, but it's going. The ratios are going down by the same amount each time. I think this is actually linear. It looks like it's going down by 35 each time. So this is just a linear model, I believe. Here, 288 divided by 320, that's 0.9. About 259 divided by 288 is about 0.9. And that one is about 0.9 as well. So yes. And because it's a fraction, this constant ratio is a fraction, it's a decay. Exponential decay. I can write the initial amount, and then the base is 0.9. And if I think about what the decay rate is, remember, if this was 1, if I think of it as this value, whoops, not my plus, it's a minus, isn't it? Minus, well, it's going down by 10% each year. If it was 100%, if it was just 1, it would stay the same, but it's going down. It's going down from 1. R is 0.1, so your decay rate is 10%. Decay by 10% per year, or per whatever. Good. Next. Okay, so this is somebody just pounded this into a TI-83, and we see some window settings here. This is the function 10 times 1.5x, so that's this one. We want to sketch a graph of this. Notice this is the initial amount. That's kind of like the A value, the initial amount, and this is the base. We see the growth rate is 50%, 0.5, which is 50% growth rate. But it is exponential growth, I can see that. They want us to sketch a graph of 40 times the same function. Well, if this is 10, we see the scale is going up by 10, then A, you start there and kind of have the same rate. Now, it's not going to have the exact same slope because everything's kind of been stretched, but it would have the same base with a new starting value, right? This is 40 here, right? And so that's that function. Compared to B, and this is A, compared to B, which has the same initial value, but a different base, a higher base. So it means it's going to have the same starting spot, but a steeper base, right? A higher growth rate. And so that means it's going to sort of go up a little bit faster, even though it's going to go through the same value there. That's 10. So this is part B, which is 10 2 to the exponent x. And of course, you could fire that into a graphing calculator to check. We're going to be doing some graphing calculator stuff this week. A population started at 5,000 and grew by 7% a year. So it's exponential growth, right? And so I know that it's going to be of this form. Oops. That form where B is going to be more than 1, right? Because it's growth. But if I think of it in this form, the R is the growth rate, right? R is 7%. So the model then is 5,000 is the amount that we start with, and then the growth rate 1 plus 1.07 to the exponent x. It's going up by 7% a year. What if the population decayed by 15% a year? Well, then we know that the B value would be less than 1. Right? We think of it this way because it's a decay rate. Here, the decay rate would be 15%. Right? We'll change that to a decimal, and then I go 1 subtract 0.15 is 0.85. And the model would be 5,000 times 0.85 to the exponent x. And then I can see that, the 0.85 represents, even though the population decayed by 15%, 85% of it stayed for the next year. All right? Good. Easy peasy. So this was one of the ones we're going to do together, which is I'm going to do it with you. Which situations represent linear growth, exponential growth? Justify your answers. A hairdresser increases the price of a haircut by 50 cents every year. So notice that we're adding 0.5. Well, adding 0.5 every year, the same amount every year, isn't a percent increase. That would, if it was a percent increase, that would be exponential growth. This is the same amount each time. This is linear growth. The investment doubles. That means multiplying by 2. That sounds a lot like exponential growth. That one's exponential. The players in each round of a tennis tournament are the winners from each pair in the previous round. Well, that sounds weird, but you know, the idea is if we start with 100 tennis players, then half of them get eliminated, then it would be 50, and then 25. Well, what's going on? This is getting divided by 2. Multiplying and dividing, that's exponential. Daryl makes $10 an hour working as a line chef. Notice that it's not a percent. He's just adding $10 to his income for every hour he works, right? Plus 10, plus 10, plus 10, plus 10. This is linear. All right. Stay tuned. Notice that there's some TI-83 stuff here, so you'll want to grab one of those and have fun with that.